Good morning and good afternoon. Good to see so many new faces today. Welcome to this webinar on power supply for large-scale electrolysis. I'm Patrick Bekel, Commercial Director of VONK. Thank you for bringing in subjects for today's webinar. For our next webinar in a couple of months' time, we're seeking companies that are interested to have a roundtable discussion with us on efficient hydrogen production. For the ones that did not participate in our previous webinar, I'm pleased to introduce Bart de Vries to you. Bart studied in the Netherlands at the Technical University of Twente. Bart studied innovation management and got his master's degree there. Bart has 15 years of experience in all kinds of energy, and in the coming webinar, he will inform you on the main design criteria of power supplies for large-scale hydrogen production. Bart, good luck and enjoy the webinar.
Thank you very much, Patrick, for the introduction. Indeed, today, in approximately the next half hour, I will inform you on our insights and our experiences on power supplies for large-scale electrolysis systems. Gained from project experiences in the past year and so. During this webinar, there's an opportunity to ask questions, which you can do through the chat screen that's on the right-hand side of your screen. We will address these questions afterwards. So, what's the agenda for today? Firstly, I will tell you a bit about our organization, VONK, and what we're doing in the field of power conversion. Then I will give you our perspective on large-scale electrolysis facilities and power supplies, as well as the choices that you have to make within this power supply. Then we go into depth and look at the various items that determine how to set up the power supply in the most optimal and efficient way. After that, we will have a short outlook to the future as we see it, and I will end with some main takeaways for you and to take home, of course. After this, we will address the questions that I mentioned earlier. Our organization, VONK, has been started in 1937 by Mr. I.M. VONK as a small electronics repair shop. Soon after, oil was discovered in its proximity, and he started to deliver electrical and instrumentation solutions there. Since then, we've grown from a local E&I supplier to an internationally recognized knowledge company in the field of power conversion, electrical and instrumentation, and control and automation. Our power conversion activities started in the 1960s within the Holec conglomerate. And since its inception, we've been involved in the development of drives for uranium enrichment. With a history and legacy in the development of important technological developments, it's only logical that we are involved in the hydrogen movement today. So when it comes to power conversion, what is it that we do? Basically, there are three pillars of activities. The first one that you can see on your left is that of drive solutions, such as for uranium enrichment and for radar drive systems. The second pillar that I want to describe to you is on the left, which consists of special power converters that we usually make for scientific institutes, for large-scale research facilities. An example of this is a 140 megawatt power supply that we are currently delivering to the Max Planck Institute in Munich for nuclear fusion research. In the middle, you can see industrial grid connections, like you would need for an electrolyzer. This is visualized in this slide for more clarity. Basically, it's a connection between a grid and the application. As VONK, we make customer optimized solutions based on standardized building blocks. These are total solutions, so not only including a transformer and a rectifier, but also items like switchgear, bus bars, and power factor compensation. With a heritage of working in many demanding industries in various applications, we know what technology is best fitting for a particular kind of application environment. And it doesn't matter what technology is required, as we've done it all before, and we will do it again for hydrogen. After this short introduction of our company, let's go to the main topic of today, which is power supplies for large-scale electrolysis facilities. First, I will give you some perspective on this, the scope of today's subject. We're not going to talk about the entire value chain from energy production all the way to green hydrogen utilization. Actually, we're going to focus on the electrical part of it. So if you were interested in the entire value chain, I'm sorry to inform you that this is probably the wrong webinar for you. I see that nobody is leaving the webinar, so I guess we're all at the correct site at the moment. To give you a better perspective on how we are approaching this subject, we've got this graphic. We're looking at the facilities as they are set up today. And in most of the cases, you can see this as displayed here. And we're looking at facilities with power levels of tens of megawatts up to several hundreds of megawatts. These are often set up with a connection to a high voltage AC grid, as you can see at the top of your screen. Then this is converted to medium voltage AC. And then there are several building blocks in place consisting of a transformer, rectifier, and electrolysis units. Within this webinar, we will focus on the transformer rectifier combination, which we sum up as the power supply. There are three main drivers that drive power supply choices in relation to achieving the optimal solution for your power supply for large-scale electrolysis facilities. These three are efficiency, power quality, and capex. Efficiency is obviously related to the amount of losses within the conversion. Or to put it in other words, how much electricity will be converted into hydrogen, and the more efficient you get, the better your OPEX performance is, or to put it more bluntly, the more bang you get for the buck. Power quality is related to the levels of fundamental power factor and harmonic distortion. During this webinar, I will combine these for simplification as harmonics. Compliance to grid code requirements is key in this aspect. The third one is capex. Even though the power supply is a relatively small part of the overall electrolyzer investment, it's still an out-of-pocket cost. The drivers that I just mentioned always are applicable in the combination of all three. However, which one of those is dominant in the mixture is depending on the application environment, as different application environments determine which one is dominant in the mixture. Basically, there are two types of application environment, which I will describe to you in this slide. Any kind of electrolyzer that you link to a public grid needs to be compliant to grid code requirements at the point of contact. If you are in an environment with less harmonic influence, for instance, when you're located at a new building site or located closely to an electricity plant, the amount of harmonics that you're being allowed with your power supply is equal to the grid code limitations. Or in other words, the grid code limitations become your minimum requirement. If your power supply is located, if your electrolyzer and its power supply is located in an environment where there is already harmonics influence from the environment, for instance, at an existing industrial site where there is limited grid capacity, or where there is already existing electrical equipment in use that's causing harmonics, you have less harmonics being allowed for the electrolyzer. This is reflected with the red bars that you can see on the left of your screen. In these kind of, so looking at the different application environments, you see that in an environment with less harmonic influence, the power quality becomes a minimum requirement, and you will focus on efficiency and capex over power quality. Whereas in an environment with more harmonic influence, power quality becomes dominant in the mixture over efficiency and capex. and this will come back in different choices that you have to make when optimizing your power supply. We will now go into depth and look at items of the power supply that determine the overall choices and the optimization. The first one to look at is that of the rectifier topology. This is the single most determining item of choices within your power supply. Choices that you make for your topology have the most impact on the overall performance of your power supply. If you want to optimize for efficiency and capex, you want a lean and mean approach. There are two common options to achieve this. The first one is a multi-pulse thyristor solution, either at 12 or 18 pulses. We see this as the best option because it's got the best efficiency and good capex performance. Another often used alternative is a diode IGBT chopper. We use it often in various applications, but we don't see it as favorable for an electrolyzer application because it's less efficient and more expensive than a multi-pulse thyristor solution. If you want optimization for power quality, then a higher pulse thyristor solution, for instance at 24 or 36 pulses, offers an improvement in terms of power quality performance. However, if you are in an environment where there's severe harmonics in play and you have stringent measures to taken into account, then an IGBT active front end offers superior power quality performance. This eliminates most of the issues altogether. And there's also no need for power factor compensation, which is the next subject that I will address. When addressing power factor compensation, I first want to explain you a bit about what power factor actually is. Power factor is the ratio between the real power, the power that you're actually consuming in your application, and reactive power caused by harmonics and phase shift. The higher the ratio, the better it is, which means the more reactive power, real power you have, and the less reactive power. In an ideal situation, you only have reactive power, only have real power and no reactive power at all, so a power factor of 1. Power factor is one of the items that you need to comply to when it comes to grid regulations. In many cases, the power supply by itself, in this case the rectifier, is not sufficiently performing to be compliant by itself. Therefore, it's a common measure to add power factor compensation. These are measures to improve this ratio and be compliant to the requirements. There are two ways in which you can apply power factor compensation. The main approach is to set it either at medium voltage or at low voltage. Medium voltage is a centralized approach, whereas low voltage is a decentralized approach. The main advantage of applying power factor compensation at medium voltage is that you can not only cover your own installation, but you can perform power factor compensation at grid level. So also when you have interfering other power supplies from other applications, you can also improve the overall performance of your local grid. There are three ways in which you can apply power factor compensation at medium voltage level. The first one is called STATCOM. That's an IGBT-based system with full dynamic compensation, and it has two main advantages. The first one is that it covers both power factor compensation as well as harmonics. So it works on both levels of compliance. The second advantage is that compared to a thyristor controlled reactor, which I will describe next, it takes less floor space. STATCOM is limited by the amount of power that it can handle. It depends a bit on the application environment, but mostly you won't get up to over several tens of megawatts in compensation, or you have to apply more in parallel. And secondly, the second downside of it is that it's quite expensive. The second option is that of a thyristor controlled reactor. In contrary to STATCOM, it can only tackle power factor but no harmonics, and it has a larger footprint compared to STATCOM, but it's cheaper. The third commonly used approach to power factor compensation is a passive harmonic filter. We don't regard this as a very suitable solution for the electrolyzer application because it lacks dynamic behavior. And obviously the electrolyzer application has dynamic behavior. So it's not the one that we would suggest. However, it's supplemental to the former two, as in case you apply a passive harmonic filter, you can lower the amount of STATCOM or thyristor controlled reactor capacity that you need, and therefore have a cheaper overall solution. The other option is to apply power factor compensation at low voltage. And this is actually the option that we prefer when possible. There are three main advantages when applying power factor compensation at low voltage level. The first one is that you can integrate it in the building blocks of your power supply. I will come back to that later. The second one is that it requires less floor space overall, so combining all decentralized power factor compensation units together when compared to power factor compensation at medium voltage level. The third one is quite simple, and that it's cheaper. From the power factor compensation, we go to the transformer. This is an item in which we have a generic approach, and we're not looking into differences between different application environments. We've got a number of best practices from experience, and the first one that I would like to zoom into is that of applying multiple rectifiers per transformer, especially for thyristor-based solutions. In many cases, where you have a single power supply in place, you often have one transformer and one rectifier. However, due to the nature of the power supply of the electrolyzers, where you have often multiple trains in series, what you can do is apply multiple rectifiers, for instance 2, to one transformer. This has the advantage that you can simulate multipulse behavior, so a power quality improvement, as well as that you have less cost. And this is basically driven because you have one transformer less. Less equipment means less cost. Second item is that has a relation between the difference in the voltage range of the electrolyzer stack between begin of life, end of life, as illustrated in the graphic that you can see on the right. What you see is that the voltage range between minimum and maximum current shifts up over time due to degradation of the electrolyzer stack. This means that the resistance goes up and the voltage required to obtain the same power level also goes up. As power supplies have their best power quality performance at top of their voltage line, at the top of their voltage, you want to increase the output voltage of the transformer. This can be done by using taps on the transformer. The third item that I want to address is a very practical one. As power supplies for electrolyzer systems have very high currents, it's a good thing to have the transformer placed closely to the rectifier, as you need to transfer the currents from the transformer to the rectifier. A lot of copper is needed, and if you place them closer together, less copper is needed, so it's a cost saving. From the transformer, we go to the cooling system. Even though our systems, as we build them, are very efficient, as you could see in an earlier screen, we can reach up to 98% of efficiency. You have to look at it as from a size perspective. For instance, if you're having an electrolyzer plant which is 100 megawatts, even at 98% efficiency, you still have 2 megawatts of heat dissipation. This obviously means cooling is an important aspect to take into account. There are two ways to deal with cooling when it comes to power supplies. Basically, these are air cooling and water cooling. While we often use air cooling, we don't see it as a sufficient measure for this kind of power levels, because the amount of surface that you would need, and therefore the amount of floor plan that you would need for this kind of cooling systems, would mean that it's practically not desirable. So we always use water cooling. For an electrolyzer plant of this size, there's always a significant cooling system in place. So a good suggestion to save on overall costs is to integrate the cooling system of your power supply with other cooling systems, which means you have to adjust and align items like cooling water flow and cooling water temperature. A question that we've often been asked about is that of the scalability of the power supply solution. To answer this question, I want to shed some light on the way we approach setting up the power supply for this kind of solution. What we do, and I mentioned it earlier during the introduction of our company, is set up our power supply solutions as a customer optimized solution based on standardized building blocks. Within doing this, the setup mechanically for the power supply is more or less the same, as well as the control electronics, which means engineering is limited. However, we optimize the power electronic components to match with the requirements of specific electrolyzer projects. What we see is that the limitations in the power electronics are far higher, or less. They have far more capacity than the electrolyzer stacks. So what we can do is match the power electronic components to the size of the electrolyzer stack. In that case, we can set up power supply building block. And if you want more capacity, it's just the same as with your electrolyzer. You just add more building blocks. From a technology point of view, thyristors are highly scalable. They are very well suited for dealing with high currents. IGBTs, however, are current limited by nature. In practice, this means that you need to apply more IGBTs in parallel to achieve the same high currents as you would have with a thyristor solution. Technically, this is not a problem. But commercially, IGBTs as components are more expensive anyway. So if you need to apply more in parallel, that means your prices also go up. This is even more applicable for an active front end, as this is a boost converter, and I won't go into technical details, but it means that your components are running at a higher current level. So the effect of having more components in parallel to achieve the same current level is emphasized even stronger. For power factor compensation, I already mentioned that having it at low voltage level is an advantage when it comes to scalability. The main driver for this is that you can integrate it within your power supply building block, which means if you want to scale to a larger scale power supply for a larger scale electrolysis facility, you just add more building blocks. However, if you apply power factor compensation at medium voltage level, for each project size and different circumstances regarding the local grid, you need to recalculate, re-engineer, and remanufacture your medium voltage power factor compensation. Another question that we've often been asked about is that of footprint. For any kind of rectifier topology, additional equipment is necessary to be compliant to power quality requirements, both towards the grid, but also towards the electrolyzer. And it differs amongst the topologies. Now, as I mentioned, I won't go into too much detail, but it has a significant impact on the overall footprint, as well as currents. And we set up a table to illustrate this a bit, because, for instance, looking at 5,000 amps of current, what you see is that an IGBT active front end requires only very little additional equipment, so therefore has a very small footprint. In comparison, a multi-pulse thyristor solution requires a bit more additional equipment and has a bigger footprint. However, looking at it at a larger level of current, for instance at 10,000 amps, what you see then is with an IGBT active front end, you would need significantly more IGBT stacks, causing the relative footprint to go up, and a multi-pulse thyristor solution probably mostly only needs larger thyristor stacks. So at that kind of current level, the relative footprint sort of evens out. In any case, the effect of the diode IGBT chopper with regards to additional equipment, as well as having requiring more IGBT stacks, is somewhat in the middle. When looking at power factor compensation, I already mentioned that applying it at low voltage results in a smaller footprint. However, applying it at medium voltage does give you some freedom at where to locate your power factor compensation units, because it can be anywhere at the medium grid, so you have a bit more freedom to play with, even though it requires more space. After going through a lot of information on the power supply as it is today, we will now have a short outlook towards the future. The main trend that we see here is towards more DC grid utilization. There are two drivers or desires behind this. And the first one is that of less conversion losses. And the second one is to be independent from the public grid. You see two types of applications here, implementations here. The first one is that of local medium voltage grid. For instance, at industrial sites where you want to accommodate multiple large-scale DC consumers, DC power supplies on a dedicated grid. The second one is of a direct coupling between a dedicated large-scale renewable source, such as a large solar farm, wind farm, or a hydroelectric plant, linked directly to a dedicated large-scale electrolysis facility. There are two main technology developments in play, which are high-power DC-DC converters, as well as multi-level modular converters, specifically applied for electrolysis systems. We won't go into too much detail on these items, as we are focused on the power supplies of today. So if you have any questions, please address them outside of this webinar, and my contact details will be displayed later. As I mentioned, we are already approaching the end of this webinar, and if you haven't paid any attention at all, here are the main takeaways, so it's still a learn for experience. As I started with, we see three main items that steer power supply choices, being efficiency, power quality, and capex, and it's always a mixture of those three. Within this mixture, the application environment determines which one is dominant and which approach you should take. We've set out 4 situations which we see as typical application environments and our approach to how to optimize your power supply in this respect. The first one is a situation with less harmonic influence, where you want to optimize for efficiency and capex. As I mentioned, this is the lean and mean approach. What we would suggest is to apply a multiple hysteresis topology in combination with power factor compensation at low voltage level. If you have a situation with more harmonics influence, we would suggest to use a higher pulse thyristor topology, again with low voltage power factor compensation. If you have a situation in which there is severe harmonics, an IGBT active front end has superior power quality performance and solves most of your problem. However, if you have severe harmonics and high currents in place, the IGBT active front end becomes a very expensive solution. Therefore, in that case, we would suggest to use a higher pulse thyristor solution with low voltage power factor compensation, as well as STATCOM at medium voltage. Because these situations are quite different in their application environments, and there are different approaches to tackle them, we would strongly suggest to have power supply experts involved at an early stage of your project development, as the choices up front definitely influence the overall outcome and return on investment on your project as a whole during the later execution stages. After talking for quite a while now, I'm really happy to address your questions, and I see that we've already got quite a few of them. And I will address the first question, which is sent to us by Toon Henmans. It's a good question. It's a question on, I mentioned that it's only a small part of the overall electrolysis cost, and he asked, how much is it per megawatt? Obviously, I don't want to turn this technical webinar into a too commercial webinar, but let's put it like this. the overall cost of a power supply is well between 20% of the overall investment. And that's a rough figure. And how much per megawatt obviously depends on how you want to apply your application. But we've seen settings in where we are well below 100, well below 100,000 euro per megawatt. Sorry, I have to phrase it correctly. Another question by Bart van der Bos. How to fault the voltage transients with mechanically switched LV capacitors? Well, this is done by switching the capacitors on the zero crossing of the current. But this is easier done by thyristor-based solutions. Hopefully this answers your question. A question by Siddharth Rayagopal, hopefully pronounced it correctly. Can we use multiple thyristors for 10 megawatts or gigawatt projects? And this is a very easy question to answer, because what you see is that the sizes of the stacks of the electrolyzer are smaller in scale of their capacity limits than our power supplies or the power electronic components is. So what you would need then, or what you would use then, is several building blocks consisting of transformer rectifier as well as electrolyzer stacks in parallel. And then you can build them up to, I would almost say, unlimited size. A question from Arnaud Rosé. What is the typical voltage range from stacks for IGBT products? Well, there are multiple voltage ranges in play, and actually the voltage range is not the limiting factor here. What's limiting is the current, and what we see is that at several thousands of amps of current, you run out of current here, and often electrolyzers require more. A question from Robert Marcus. What is low voltage and medium voltage? Well, low voltage we regard most below 1000 voltage, and anything above as medium and high. And high voltage being the point of connection to a public grid, which is often at 66 kV or even higher. A question from Hans Lammers. Do you see the expert effects on the A side that originate actually from the electrolyzer? Yes, this is actually the harmonics as we discussed them today, and this is why you need a power factor compensation. Have we tackled most of the questions now? Yeah, I think we've gone through most of the questions for now. So if any further questions, feel free to ask them and contact me directly. No problem at all. So for now, I would like to thank you very much for your attendance today. It's been a pleasure for me to present this webinar to you, and hopefully I talk to you soon or at the next webinar. Thank you very much and enjoy your day.